Welcome to The Explainer. Today we're diving into a cosmic mystery, a real head-scratcher that pits the absolute strongest force in the universe against one that seems, well, almost impossibly weak. How can both of those things be true at the same time?
Okay, let's start with just one number, 67. That's how many zeros you would have to write after a 1 to describe the power gap we're talking about. I mean, it's a number so ridiculously huge, it makes the number of atoms in our galaxy look tiny. And it represents a massive puzzle in how we see the universe. So yeah, that's the big question, right? How can the universe's most powerful force also be one of its weakest? It sounds like a total contradiction. But, as we're about to see, the answer isn't just possible, it's actually woven right into the fabric of reality itself. All right, let's get right into it. We've got to meet the two main players in this cosmic drama. Two forces that seem to operate on completely different levels, almost like they belong in different universes.
On one side, you've got the Planck tension. Just think of this as the universe's ultimate breaking point, the absolute maximum force space-time can even handle. Then on the other side, you have the QCD string tension. Now that's the force that literally glues protons and neutrons together. And yeah, it's super strong up close, but on the cosmic scale, it's weaker by that mind-blowing factor of 10 to the 67th. How on earth can these two things even be related?
So, where do we even start? Well, the first clue is a really wild idea. A fundamental force doesn't just have one fixed strength. Its power actually changes depending on the distance, the scale, you're measuring it from. This idea has a name, of course. Physicists call it the running coupling, and it's pretty simple when you break it down. A force's strength isn't set in stone. It runs, it changes, depending on how far away you are. So a force that seems crazy powerful up close might look totally different from far away. And this isn't just random. There's a rule book for how this works, something called the beta function. And for the force we're interested in, the rule is surprisingly simple. Its strength fades in proportion to its own strength squared. And that squared part, that's the secret sauce. It means the force doesn't just get a little weaker, it gets weaker exponentially faster the farther out you go.
Okay, so we've got the math, but why does the universe play by these rules? The physical reason is, well, it's actually something you can wrap your head around. It has nothing to do with exotic, weird particles, but everything to do with plain old probability.
Picture this. Force isn't traveling through something smooth and solid like a steel cable. Nope. Imagine it's more like it's hopping between tiny little grains, kind of like a string of beads. For that force to get from point A to point B, the connections between all those little grains have to hold up. Here's how that works. For this force chain to hold together, it's got to make connections, right? So if the chance of making one good connection is, say, P, the chance of making two independent connections at the same time is P squared. The odds just plummet. The farther you go, the more connections you need, and the probability of all of them holding together drops off quadratically. The force just fizzles out. And what do you know? That's exactly what the beta function told us would happen. All right, so we've got our motive, this idea of a changing scale. And we've got our mechanism, this game of probability with granular connections. Now let's put it all together. Let's build the mathematical proof and see if we can finally crack this case.
This is it. This is the equation that ties it all together. It lets us take the force's strength at the absolute tiniest scale you can imagine, the Planck length, and then calculate what it should be at the much, much larger scale of a proton. That ln part, the logarithm, that's just a fancy math tool for handling that massive jump in distance we've been talking about. So what happens when we actually plug in the numbers? You start with what we know about the stiffness at the Planck scale. You factor in that huge leap in distance to the scale of a proton, and look what happens to the bottom of that equation. It becomes this teeny tiny fraction.
And here's the payoff. This is the moment we've been waiting for. When you divide the original force by that tiny little fraction, you get a huge result. We convert it to the right units, GeV squared, which is just the language physicists use to talk about this stuff, and we get a value of about 0.2. And that number? It's a perfect match for the force that scientists actually measure holding protons together. The math works. The theory isn't just a theory anymore. So there you have it. We've actually bridged that insane 67 order of magnitude gap. That cosmic contradiction we started with, turns out it's not a contradiction at all. So let's get to the final reveal. So that force holding our world together, it's not some different, weaker force. It is the strongest force in the universe, the super strong Planck tension. We just experience it as weak because it's been diluted across an unimaginable distance, faded by the sheer improbability of it holding itself together at our scale. It's a pretty profound idea, really, and it leaves you with one last thought. If one of the most fundamental forces of nature is really just a matter of probability and perspective, if its very identity changes depending on your point of view, what other cosmic truths are out there that we're simply looking at from the wrong scale?